All right, so today we're going to introduce uh, the idea of voltage. Measured in volts, it's what, we buy some batteries based on. We know, like, if we ever travel overseas, we need to know the voltage that their, kind of house electricity is based off of. So to do that, we're really going to talk about what are we talking about when we're talking about voltage. And really, voltage is kind of just this potential difference. So last time we talked about electrical potential energy. So the phrase we're using here is potential difference. Um, so kind of looking, kind of going back to, I've got two charged plates, one positive, one negative, electric field lines going from the positive to the negative. Um, the formula for electrical potential energy was negative QED. And so far, the unit for electric field we've been using is newtons per coulomb. And that's great. That still works just fine. Um, really what we're going to see for voltage or the change in kind of electrical potential is it's going to be negative the electric field, the strength of the electric field times how far apart those plates are. So the potential difference essentially tells me, like, what is my change in voltage? What's my change in potential if I put a positive charge right here at the top and it moves all the way down? What's my change in potential there? So another way that we can kind of look at it is, negative ED, negative QED. Essentially, I can replace negative ED here in the potential energy equation. Make a better delta there. Maybe a better potential energy equation might be Q, change of potential. This means the actual change of potential energy, it's based on the specific charge that I'm putting within an electric field with a set potential difference. It's kind of a shortcut that we can take. Like, we don't always have to come back to measuring the electric field and measuring the distance between two charged plates. If I just know the potential difference, between the two plates, then I can just use, voltage here. Um, One of the things to note here, like, if I solve for just the electric field here, so the electric field would be equal to the negative change in voltage over distance. My unit for electric field, if I just solved for E there, would be volts per meter. So I think that's kind of becomes a little bit interesting. Like, electric field, we can get the quantity in two different ways, and we get two different labels for it. And then that just goes into the fact, like, newtons is a combination, it's derived units of kilogram meters per second squared. And voltage now is this combination of, newtons per coulomb. We got meters in there. Looking at the units, I just find that kind of interesting. Uh, Really, the big equations that are going to be important for practice problem stuff like that are going to be that one and that one. The one I'm going to practice using, though, is going to be this one here. And as you can tell, it's a three variable equation. So chances are it's going to be pretty basic what we're going to do. All right, so practice problem there at the bottom. So we've got two charged plates. And in this case, we're going to say that they are separated by 15 centimeters. And just like always, we are not leaving centimeters. Got to convert that to meters. So in this case, move my decimal 1, 2 to the left there. So I've got 0.15 meters. And the electric field that exists between these two plates, the uniform electric field, I should say, is 360 newtons per coulomb. All right, and really all we want to know is what's the potential difference between these two plates, essentially. What's the potential difference I would measure as a charge moves across the electric field from one plate to the other? So this one's actually going to be pretty easy. So I know that the change in voltage is equal to negative the strength of the electric field times the distance between them. In this case, I've got negative 360 newtons per coulomb times the distance between them, which is 0.15 meters. Right, so now when I come through here and open up my calculator, let's go ahead and clear that out. So I've got negative 360 times 0.15 meters. And my voltage difference, my potential difference is going to be negative 54. And we could go with newtons meters per coulomb or kilograms per kilogram meter squared per second squared coulomb squared. Really though, the unit we're going to use, this change in V is really important because essentially my unit here is just voltage. My potential difference here is negative 54 volts. So that's pretty easy. So now if I know the charge I'm going to place in here, if I know the charge, like let's say I put a 3 coulomb charge in there, a positive 3 coulomb charge about right here, right at the top here, I would just take this times positive 3, and that would get me my potential energy, my electrical potential energy. It's pretty basic, pretty easy. This is probably the shortest video we've had for a while. Probably will have for a long time as we continue looking at electricity, how charges move. Because chances are, if we're talking about voltage now, we're going to be talking about current and resistance pretty soon here. But anyway, that's potential difference. Those are kind of the multiple ways that we can find potential difference, and then where we can actually use that in some other equations, stuff like that. But good luck with the practice.